Welcome! In this session, we're diving into problem number 1387, sort integers by the power value. We'll explore the problem statement, break it down step by step, and review strategies to solve it efficiently. Let's get started. In this problem, we are tasked with sorting integers based on their power value. The power value of an integer x is determined by the number of steps it takes to reduce x to 1 using the following rules. If the number is even, divide it by 2, if it's odd, multiply it by 3 and add 1. For example, if x is 3, the sequence is 3, 10, 5, 16, 8, 4, 2, 1. This process involves 7 steps, so the power value of 3 is 7. Now, given a range of integers defined by two values, low and high, we need to sort all the integers in this range based on their power values. If two integers have the same power value, we then sort them numerically. Finally, we return the kth integer in the sorted list, where k is a 1-based index. The input for this problem consists of three integers, low, high, and k. The range, low, high, specifies the integers we need to consider, and k indicates the position in the sorted list of integers that we need to return. The constraints ensure that low and high are between 1 and 1000, and k is at least 1 and at most the total number of integers in the range, low, high. The output is a single integer that represents the kth smallest integer in the sorted list according to the power value and the tiebreaker of numerical value. This setup ensures the problem is well defined and has a unique solution. Let's consider the first example to illustrate how this works. The input is low equals 12, high equals 15, and k equals 2. This means we are looking at the integers 12, 13, 14, and 15. First, we calculate the power values for these integers. 12 has a power value of 9, 13 also has a power value of 9, 14 has a power value of 17, and 15 has a power value of 17. After sorting these integers by their power values, we get the list, 12, 13, 14, 15. Since k is 2, we return the second integer in this sorted list, which is 13. This example highlights how power values are calculated, how sorting is performed, and how the kth integer is selected. Now, let's analyze another example. Here, the input is low equals 7, high equals 11, and k equals 4. The integers in the range are 7, 8, 9, 10, and 11. Calculating their power values, we find that 7 has a power value of 16, 8 has a power value of 3, 9 has a power value of 19, 10 has a power value of 6, and 11 has a power value of 14. Sorting these integers by their power values gives the order 8, 10, 11, 7, 9. From this sorted list, the fourth integer is 7, so the output is 7. This example underscores the importance of sorting by power value first and then numerically when there are ties. In solving this problem, we need to account for some important considerations. The range, low, high, can include up to 1000 integers, so efficiently calculating the power value for each number is critical. This can be optimized using techniques like pre-computing or caching power values to avoid redundant calculations. Sorting the integers involves comparing their power values and, when ties occur, their numerical values. Edge cases to handle include scenarios where low equals high, meaning the range contains only one number, and cases where multiple integers share the same power value, requiring careful secondary sorting. These constraints and edge cases ensure the solution is both efficient and robust. To start, the brute force approach involves directly computing the power value for each integer in the given range, low, high. The intuition here is straightforward. For every number, we simulate the transformation rules iteratively until the number reduces to 1. Specifically, if the number is even, we divide it by 2, if it's odd, we apply 3x plus 1. Once we have the power values, we store them as tuples of the form, power value, integer. Sorting these tuples first by power value and then by the integer provides the desired result. However, this method comes with some trade-offs. It's simple to implement, but computationally expensive, especially for large ranges, because we redundantly recompute power values for numbers that appear multiple times in the transformation sequence. The time complexity here is driven by the cost of calculating power values for all numbers in the range and sorting the results, resulting in an overall complexity of O, height low, asterisk log, max, low, high. While easy to understand, this approach doesn't scale well for larger input sizes.
A more efficient strategy is the optimized approach using memoization.
Here, the key insight is that power value computations often overlap. For instance, calculating the power value of 6 involves the same steps as 3 at a certain point. By storing already computed power values, we avoid recalculating them, saving time. This is achieved by using a dictionary or array to memoize results. For each number in the range, we compute its power value recursively, checking the stored results to reuse any pre-computed values. Afterward, we store the results as tuples and sort them just like in the brute force approach. The major advantage here is that memoization significantly reduces redundant calculations, making the algorithm much faster for larger ranges. The time complexity is now O, high-low, plus M, for computing power values, where M is the number of unique numbers encountered, plus the O, and asterisk log, N, for sorting. While this approach is slightly more complex to implement than brute force, the improved efficiency makes it a worthwhile trade-off for larger ranges.
Another option to consider is pre-computing power values for a broader range of numbers. This approach is especially useful when we expect multiple queries over different ranges in the future. The idea here is to pre-compute power values for all numbers up to a maximum threshold, such as 10,000, and store these results in a dictionary or array. Then, for each query, we can simply retrieve the pre-computed values and sort them directly. The main advantage is that this eliminates the need to recompute power values entirely, making it extremely fast for repeated queries. However, the trade-offs are significant. Pre-computing requires additional memory to store all these values, and the one-time pre-computation step itself is costly, taking O, M asterisk log M, for M numbers. Thus, while this approach excels in scenarios with repeated queries, it is inefficient for one-time computations due to the upfront cost and memory usage. The chosen strategy for this problem is the optimized approach with memoization, as it offers a balanced solution in terms of efficiency and simplicity. By storing previously computed power values, we avoid redundant calculations, significantly improving performance for larger ranges. Unlike pre-computing, this method does not require excessive memory, making it well-suited for one-time computations. One key insight that makes memoization effective is the observation that the transformation rules often lead to overlapping calculations for different numbers, such as the sequences for 6 and 3. Memoization allows us to reuse these intermediate results, saving computation time. Once the power values are computed efficiently, sorting by power value and integer becomes straightforward. While brute force is too slow for larger inputs due to repeated calculations, and pre-computing is overkill for a single query, memoization provides the right balance. It's efficient, scales well with input size, and avoids unnecessary memory overhead, making it the most practical choice for this problem. To solve this problem, we need to sort integers in the range, low, high, based on their power values and return the kth smallest number after sorting. The power value of a number is computed by repeatedly applying two rules. If the number is even, we divide it by 2, and if it's odd, we multiply it by 3 and add 1. This process continues until the number becomes 1, and the total number of steps taken is the power value. Before diving into the algorithm, we first need to ensure that the input is valid. Specifically, the range, low, high, must be such that low is less than or equal to high, and the value of k must fall within the range, 1, high, low plus 1. These checks are crucial to avoid errors like invalid ranges or out-of-bounds indexing later in the process. Next, we pre-compute the power values for efficiency. To avoid redundant calculations, we use a dictionary called power_cache to store the power values of numbers that have already been computed. This is where memoization comes into play. We define a recursive helper function compute_power, n, to calculate the power value of a number. If n is 1, we return 0 because no steps are needed. If the power value of n is already in power_cache, we simply return the cached value. Otherwise, we compute the power value recursively. If n is even, we calculate the power for n/2, and if n is odd, we calculate the power for 3 asterisk n plus 1. In each case, we add 1 to account for the current step and store the result in power_cache. Once this function is ready, we iterate through all numbers in the range, low, high, compute their power values using compute_power, and store the results as tuples, number, power, in a list. Finally, we sort this list of tuples based on two criteria: first by power value, and if there are ties, by the numerical value of the numbers. Python's sorted function with a custom key makes this step straightforward. After sorting the numbers by their power values, we can easily retrieve the kth smallest number. Since the sorting ensures that the numbers are arranged in increasing order by power value and then by numerical value, we simply pick the tuple at index k1, adjusting for 1-based indexing, and return the number part of the tuple. This gives us the desired result efficiently. Along the way, we leverage two key insights. First, memoization significantly reduces redundant calculations, especially when the transformation sequences overlap for different numbers. Second, the custom sorting ensures stability, so numbers with the same power value are correctly ordered by their numerical values. We also handle important edge cases, such as when the range contains only a single number or when k is very small. These considerations ensure the algorithm is robust and handles all inputs gracefully. The algorithm relies on a couple of key data structures to achieve its goals. The first is the dictionary power_cache, which stores the power values of numbers as we compute them. The keys are the integers, and the values are their corresponding power values. This structure is central to the efficiency of the algorithm because it prevents repeated calculations for the same numbers. The second data structure is a list of tuples, where each tuple contains a number and its power value. This list is used to store the results for all numbers in the range, low, high. Once populated, it facilitates both the sorting step and the retrieval of the kth smallest number. These data structures ensure that the algorithm is both time and space efficient while remaining easy to implement and maintain. Finally, let's analyze the complexity of the algorithm. For time complexity, the computation of power values dominates. Each number's power value is computed only once, and since the transformation sequence involves dividing the number by 2 repeatedly, the sequence has a logarithmic upper bound. For all numbers in the range, low, high, this gives a time complexity of O, high, low plus 1, log, max_number. Sorting the list of tuples adds another O, n log n, where n is the number of elements in the range. Combining these, the overall time complexity is O, n log, max_number, plus n log n. For space complexity, the power_cache dictionary stores power values for all numbers encountered, which requires O, high, space in the worst case. The list of tuples also requires O, n, space. Therefore, the total space complexity is O, high. These complexities ensure that the algorithm performs well even for large input ranges, thanks to the memoization and sorting optimizations. This code solves the problem of sorting integers by their power value using the Collett's conjecture rules. First, we define a helper function power_value that computes the number of steps required for a given number to reach 1. The computation follows the rules of dividing by 2 if the number is even and multiplying by 3 and adding 1 if odd. Next, we iterate through the range, low, high, and calculate the power value for each number, storing both the power value and the number itself as a tuple in a list called power_list. This is done to preserve both sorting criteria, first by the power value, and then by the number in case of ties. After constructing the list, we sort it. Python's default tuple sorting ensures that it first sorts by the first element in the tuple, power value, and then by the second element, the number itself, in case of ties. Finally, we return the kth smallest number, accounting for 1-based indexing, by accessing the appropriate tuple in the sorted list and retrieving the number. The algorithm is efficient for small ranges due to its straightforward computation and sorting. Edge cases, such as low == high or very small ranges, are naturally handled by the loop and sorting logic. Here, we start by importing the necessary packages, such as java.util, to enable the use of data structures like hashmap and ArrayList. Within the solution class, the method getKth is defined to find the kth smallest integer in the range, low, high, when sorted by their power values. To calculate the power value of a number efficiently, we use a lambda function and a memoization technique. A hashmap called powerValueCache stores the power values of numbers that have already been computed. Inside the method, we define an inner function called powerValue that recursively calculates the number of steps required to reduce a given number n to 1.
If the number is even, it follows the n/2 operation, otherwise, it applies the 3n plus 1 operation. The calculated steps are then stored in the cache to avoid redundant computations. Next, we create a list of integer arrays, where each array holds a number alongside its corresponding power value. Using a for loop, we iterate through all numbers in the range, low, high, compute their power values using the power value function, and store these pairs in the list. Afterward, we sort the list based on the power values, and if two numbers have the same power value, they are sorted by their magnitude. This ensures the correct order for the subsequent retrieval. Finally, once the list is sorted, we return the kth smallest number based on the specified order. Since the list is zero-indexed, we access the element at position k1 and extract the number from the second element of the array. This concludes the implementation of the getKth method. By integrating memoization and sorting, the algorithm efficiently calculates and retrieves the desired number, even for larger ranges. This approach ensures that the power values are computed only when necessary, significantly optimizing the performance. To solve the problem, we begin with the first example, getKth 12, 15, 2. The first step is to compute the power value for each number in the range, 12, 15. The power value measures how many steps are required to reduce a number to 1, following specific rules. If the number is even, we divide it by 2. If it's odd, we replace it with 3 asterisk n plus 1. For each number, we repeatedly apply these rules until reaching 1. For instance, the power value for 12 is 9 steps, as it follows the sequence 12, 6, 3, 10, and so on, until 1. Similarly, 13 also takes 9 steps, 14 takes 17 steps, and 15 also takes 17 steps. Once calculated, we pair each number with its corresponding power value, resulting in the list 9, 12, 9, 13, 17, 14, 17, 15. Next, we sort the list of pairs based on 2 criteria. First, we sort by the power value in ascending order. If two numbers have the same power value, we then sort by the numbers themselves in ascending order. Applying this to our list gives us the sorted order 9, 12, 9, 13, 17, 14, 17, 15. Once sorted, we locate the kth smallest element in this list, where k equals 2. The second smallest element is 9, 13. Therefore, we return the number 13 as the final output for this example. Now, let's move to the second example, getKth 1, 10, 4. Once again, the first step is to compute the power value for each number in the range 1, 10. For example, the power value for 1 is 0, as it's already 1. For 2, it takes 1 step to reach 1, and for 3, it takes 7 steps. Continuing this process for all numbers in the range, we obtain their respective power values. For instance, 4 takes 2 steps, 5 takes 5 steps, and so on, up to 10, which takes 6 steps. After computing, we pair each number with its power value, resulting in the list 0, 1, 1, 2, 7, 3, 2, 4, 5, 5, 8, 6, 16, 7, 3, 8, 19, 9, 6, 10. Sorting this list, first by power value and then by number, gives 0, 1, 1, 2, 2, 4, 3, 8, 5, 5, 6, 10, 7, 3, 8, 6, 16, 7, 19, 9. From the sorted list, we now identify the kth smallest element, where k equals 4. The fourth smallest element in this list is 3, 8. Hence, we return the number 8 as the final output for this example. With that, the result for getKth 1, 10, 4 is 8. Let's examine one more example to solidify the approach. This time, we are solving getKth 7, 11, 1. As before, the first step is to calculate the power values for each number in the range 7, 11. For instance, 7 takes 16 steps, 8 takes 3 steps, 9 takes 19 steps, 10 takes 6 steps, and 11 requires 14 steps to reach 1. Pairing these numbers with their power values gives us the list 16, 7, 3, 8, 19, 9, 6, 10, 14, 11. Finally, we sort the list of pairs based on power value and number, just as before. The sorted list is 3, 8, 6, 10, 14, 11, 16, 7, 19, 9. From this sorted list, we locate the kth smallest element.
When k equals 1, the first smallest element is 3, 8. Therefore, we return the number 8 as the final output for this example. This concludes the process for get kth 7, 11, 1, where the result is 8. By following these steps, computing power values, sorting the pairs, and selecting the kth smallest element, we can solve the problem efficiently for any given range in k. To analyze the time complexity of our solution, we start with the component of calculating the power value for each number in the range low, high. The function power_value, n, computes the power value by repeatedly applying the Collatz transformation until the number reduces to 1. In the worst case, this sequence can involve a number growing large initially, especially when it is odd, before eventually reducing through having steps. On average, based on the Collatz conjecture, the sequence length is approximately proportional to O log n, because having steps dominate the process. Since there are high, low plus 1 numbers in the range, calculating the power value for each number leads to a total cost of approximately O high, low plus 1 asterisk log n. Next, we need to consider the cost of storing the power values. For each number in the range, low, high, we calculate its power value and store it as a tuple, power_value, number, in a list. This step is linear in the number of elements, so it contributes a time complexity of O, high, low plus 1. Once the list is populated, we sort it. The sort function sorts the list of size m equals, high, low plus 1, by power value and then by number. Sorting has a time complexity of O, m asterisk log m, which, for our case, is O, height low plus 1, asterisk log, height low plus 1. Finally, accessing the kth smallest element in the sorted list is a constant time operation, O, 1, as it involves simply indexing into the list. Combining these components, we now have an understanding of the time spent on each individual step. When we combine all these steps, the total time complexity of the solution is the sum of the individual components. Calculating power values contributes O, height low plus 1, asterisk log n, storing the values adds O, height low plus 1, and sorting contributes O, height low plus 1, asterisk log, height low plus 1. Adding these together, the total time complexity becomes O, height low plus 1, asterisk log n, plus O, height low plus 1, plus O, height low plus 1, asterisk log, height low plus 1. For simplicity, we can express this in a more concise form. Since the dominant factor is height low plus 1, the time complexity simplifies to O, height low plus 1 asterisk, log n plus log, height low plus 1. This gives us a clear picture of how the time cost grows as the input range increases. Now let's analyze the space complexity. The primary storage requirement comes from the power_list, which holds a tuple, power_value, number, for each number in the range low, high. The space required for this list is proportional to the number of elements in the range, which is O, high, low plus 1. Within the power_value function, a variable n is used to compute the Collatz sequence for each number. This is a constant space operation, as no additional data structures or recursion are involved, contributing O, 1, to the space complexity. Additionally, the sorting step uses Python's timsort algorithm, which requires temporary space proportional to the size of the input list. This adds another O, high, low plus 1, to the space complexity. Combining these, the dominant factor remains the storage of the power_list, leading to a total space complexity of O, high, low plus 1. Finally, let's compare this approach to a brute force method. A naive implementation would involve generating and storing the entire Collatz sequence for each number in low, high. This would drastically increase both time and space complexity, making it impractical for larger ranges. In contrast, the current optimized solution computes only the power value for each number and avoids storing the entire sequence. The time complexity is dominated by the computation of power values and sorting, while the space complexity is limited to storing the power_list. Looking at best, average, and worst cases, the time complexity remains consistent. In the best case, all numbers have small Collatz sequences, but the complexity remains O, high, low plus 1, asterisk log n. In the average and worst cases, the sequence lengths and sorting dominate, but the time complexity simplifies to O, high, low plus 1, asterisk, log n plus log, height low plus 1. This ensures the solution is efficient and scalable for a wide range of inputs. Here, we explore some common mistakes to watch out for when solving the sort integers by the power value problem. First, incorrect base case handling is a frequent issue. If the stopping condition for when the number becomes 1 is not properly implemented, it can lead to infinite loops or wrong power values. Always ensure this base case is clearly defined. Next, inefficient recomputations can significantly increase runtime. For instance, repeatedly calculating the power value for the same numbers during the simulation is unnecessary. Using memoization to store intermediate results can eliminate this redundancy. Additionally, handling bounds improperly is another source of errors. Misinterpreting the range, low, high, such as including high when it should be exclusive, or accidentally skipping low, can cause incorrect results. Double-checking inclusivity and exclusivity in the range is crucial. Overflow in large numbers is another point of concern, especially in languages like C++ or Java where the transformation 3*n+1 can exceed the integer limits. Using larger data types or explicitly managing large values is essential. Finally, missing edge cases, such as when low equals high or when the range is very small, can lead to bugs. Always test thoroughly with edge values to ensure your solution is robust. Now let's focus on some insights specific to interviews. This problem often tests your understanding of dynamic programming or memoization. The key is recognizing overlapping subproblems, where the same intermediate numbers appear in different sequences. Leveraging this insight to optimize the brute force approach is critical. Interviewers may also ask you to discuss ways to improve the naive solution. For example, pre-computing results for all numbers up to the maximum possible range can save time during the main computation. Alternatively, using priority queues for sorting based on power values is another optimization technique to be prepared to discuss. Additionally, be ready to explain trade-offs. For instance, while memoization significantly reduces runtime by avoiding redundant calculations, it does require additional space. Understanding and articulating these trade-offs is essential in interviews. Lastly, always dry run your algorithm with small examples. This not only helps to verify correctness but also demonstrates your thought process and attention to detail in ensuring the efficiency of your solution. Next, let's look at related problems that can help deepen your understanding. First, the core problem itself, sort integers by the power value, is directly linked to everything we've discussed. Then, there's the Fibonacci number problem, where memoization is used to avoid recomputation, just like in our current problem. Climbing stairs is another example that emphasizes dynamic programming and the concept of overlapping subproblems. Finally, ugly number 2 involves generating numbers from a sequence based on specific rules, which is conceptually similar to the transformations we perform in this problem. Exploring these related problems can reinforce the key concepts, such as optimizing with memoization, understanding dynamic programming patterns, and efficiently managing sequences. Lastly, let's discuss some alternative approaches to solving this problem. One approach is pre-computing results. By calculating power values for all integers up to high in advance and storing them in a dictionary or array, you can achieve lookups during sorting. However, this comes with a trade-off, as additional pre-processing time and space are required. Another method involves using a priority queue, or min-heap, for sorting based on power values. This is particularly effective when you only need the top k elements, as it reduces sorting overhead. The trade-off here is slightly higher memory usage due to the heap structure. Finally, an iterative bottom-up dynamic programming approach can be employed. Starting from 1, you calculate power values iteratively for all numbers in the range, using previously computed results to build new ones. While this approach is more space-efficient than memoization, it may require additional logic to handle the range correctly. Each of these methods has its own advantages and trade-offs, so you can choose the one that best fits the problem's requirements and constraints. Great job following along. Today, we tackled the problem sort integers by the power value, breaking it down and analyzing different approaches. Remember the importance of simulation and optimization when solving similar problems. Thanks for watching, and don't forget to like, subscribe, and stay tuned for more problem-solving sessions. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!